Okay, so today we're going to talk about the last section of Notes for Chapter 7, 7.8, Improper Integrals. And so the reason we're going to call these improper integrals is because they're going to look a little bit different than the integrals we've been doing before. They're going to be what looks like a definite integral, but in one type, in one bound, we might be approaching negative infinity. Okay. Since our definite integral needs to have two definite bounds, or at least the representation of two definite bounds, remember all the way back in limits, when we're not supposed to plug in infinity into some function, we need to change the notation for this. We're not going to change the way we're going to evaluate it, but we are going to change the notation so that we say, all right, c is a constant. Let me describe the lower bound now as, instead of negative infinity, some number that will approach negative infinity, or some variable. So now my integral will go from a to constant c. Okay, this is just notational and just has to do with the fact that we cannot, technically, since infinity is not a number, we can't plug this into whatever function comes out of our integral. So instead, we're going to notationally replace it with a variable and then take the limit as that variable goes to negative infinity. The same can happen if we are integrating some integral from c to infinity. So for some constant up to positive infinity, we can instead replace that upper bound with a new variable, and it doesn't really matter what variable you choose. I'll choose b here, as long as it's not a variable that's somewhere already used. So don't use x, y, probably not z. A, b, and c are usually pretty good if they're not already somewhere in our problem. Okay, and so I'm going from c to b, my upper bound. Okay, so that's what to do if you have one bound that is, you're integrating to infinity. And the cool thing I find about this is what that means is I'm really adding up an infinite area, but yet sometimes that infinite area or that limit will converge to one value. Sometimes it will not. Sometimes it will diverge. We will get an infinite area. But sometimes this area is limited by kind of like an upper bound. We will also come back and think about this concept when we talk about series and sequences, and how a series, an infinite sum, or a series, an infinite sum, might actually converge to one number. But let's see an example. So I am going to integrate, okay, from negative infinity to negative 1 of x e to the negative x squared dx. Okay, so again, thinking about preparing for this Chapter 7 test, I look at this and I see that I could substitute this for u, because the derivative is in effect right here. So if I let u equal negative x squared, you know what, I'm getting ahead of myself. I want to go jump to this integration first, but we'll come back to that in a second. The first thing I need to do is rewrite my integral with a limit. So this integral is equal to, I'm going to choose a. So a approaches negative infinity of the integral from a to negative 1 of x e to the negative x squared dx. Okay, because I've changed my notation, now I'm ready to evaluate this like a proper integral. Okay, all right, so now I will let u be equal to negative x squared and du be equal to negative 2x dx. For those of you who are still struggling a little bit with u sub and what constants to put outside, don't forget that you can just divide that constant to the other side. So negative 1/2 du equals x dx. And think about replacing x dx, which is what's in our integral here. Okay, so this limit, okay, all right, well, let's just make sure, okay, that this limit will still hold true. And this is where you have to be really careful about our notation if we're going to do a u sub. So the top bound is a little bit easier to evaluate. Okay, so if I let x be -1, I, in fact, still get -1. Okay, so my integral will still start with -1. And I will still put a down here, but that might change where my limit is going. If I plug a in here, and let a go to -infinity, well, that's still going to -infinity. So just had to double check that my bounds actually didn't change if I wanted to do a U-sub. If you are more comfortable with an integral like this that's a little bit easier to evaluate, skipping right to the integral step, or once you have integrated, feel free. I've got my -1/2. Okay, so notice that I am continuing my limit notation because that is important. Okay, and then I've got integral of e to the u is e to the u. A to -1. Okay, so again, I have not evaluated my limit yet, so I'm not ready to get rid of it. And I'm going to plug in my bounds, so I'm going to get e to the -1 minus e to the a. Okay. All right. So now I want to start plugging in this limit. You can think about graphing this by itself if you need to, but this is definitely a chapter where we need to start thinking about our limits again. So if you need to remember, the graph of e to the x looks something like this. Okay, and so as a, or x, goes to -infinity, this will go to 0. So my final answer will be -1/2 times e to the -1, or if you'd like to simplify it a little bit more, I will have -1 over 2e. And that is my final answer. So in fact, this improper integral, where we're integrating this function from -infinity up to -1, in fact converges. Okay, so our conclusion is that this converges, and specifically converges to this value. Okay. All right, another example might be is if both of your bounds are infinity. Okay, if this is true, okay, if I have an integral from -infinity to infinity of some function, okay. Also, I apologize. PJ is being very needy. She's right next to me. Then what I'm going to do is I need to split it into two integrals. You get the choice of where you would like to split it. As long as it is not another sort of discontinuity in the middle, God forbid that there are 3 discontinuities, or we're integrating from end behavior to discontinuity to end behavior. That would be annoying. But pick somewhere kind of smart. I usually like to pick something like 0, or if you've got some kind of factor in there that might give you 0, if you plug in a certain number, pick that one. But I would need to change this into 2 different integrals. So I would want to start with a limit for -infinity and go from a, I'm going to choose 0, and then add that on to, and choose a different variable for this, because we're going to be evaluating these at the same time. So we don't want to choose like a and have a go to -infinity in one place and a go to positive infinity in another place. That doesn't really make sense. So choose a different variable for the second integral and go from the same location you chose before. Okay, that way you're just kind of dividing this area in half somehow. Okay, and go up to p, which is positive infinity. Okay, so if you've got your bounds are both infinity, you're integrating over the entire domain, entire real numbers. This can still be convergent, but we're going to have to, in order to evaluate it, we need to split it up into 2 separate limits. So let's see this example together. So let's say I have the integral from -infinity to infinity of 1 over 1 plus x squared dx. Ooh, already I see that I should be recognizing some inverse trig. This is one of our rules. So when I evaluated this, it's probably going to use arctangent. So let's set up our limits. Okay, so I will let a go to -infinity and be the integral from a, and I'll choose 0 again. 0 is a good number to plug in. This will also require that you know how to evaluate inverse trig values. So make sure you're brushing up on that. Okay, and I'll let b go to positive infinity from 0 to b. Okay, I don't need to make any substitutions because I recognize that these are both rules. These are a little tedious because you have to keep writing the limits until you've evaluated them. But this really helps keep you organized, I think is the best thing. Okay. All right, so one more time, plugging in my bounds. The limit as a goes to negative infinity of arctan of 0 minus arctan of a plus the limit, oh no, I'm going to run out of room, b goes to infinity of arctan of b minus, arctan of 0. Here we go. Okay, so here's where it comes in where we need to know what is happening. Where does tangent equal 0? Okay, remember that's what our inverse trig is really asking us. Where does this function, tangent, equal 0? And remember, arctangent is only defined in the fourth and first quadrants. So arctan is going to be 0 at 0. Okay, you can also think about it, where is sine equal to 0? Because tangent is sine over cosine. Okay, and then what happens as arctangent approaches negative infinity? Okay, and this is where you have to know a little bit about the graph of arctangent. Okay. All right, so the graph of arctangent looks a little bit different than the graph of sine and the graph of arctangent looks a little different than the graph of arcsine or arccosine because the graph of tangent has vertical asymptotes. So the graph of arctangent has horizontal asymptotes. And those horizontal asymptotes appear where tangent would have had its vertical asymptotes. So that's at negative pi over 2 and pi over 2. So this is minus negative pi over 2. Okay, let's evaluate the other one. Again, as we approach positive infinity, we will also approach pi over 2. And then arctangent of 0 is, once again, 0. So when I put those together, I get pi. So we have evaluated this integral over all the real numbers and found that the area completely adds up to pi. Now some of you might be looking at the graph of arctangent and thinking, why doesn't the area under arctangent equal 0? Well, remember, we're not finding the area under arctangent. We're using arctangent as kind of the evaluation points. But we're finding the area under this curve. Okay, so that doesn't look the same as arctangent. So remember, we're finding the area under what was inside our integral. This is just helping us evaluate, plug in some boundaries for that area. Okay. All right. One last thing, okay, is what if we are integrating around a discontinuity for a function? Okay. So let's say, for example, I had the integral from 0 to 1 of 1 over x. Okay, well, this is not as obvious as the other ones. The other ones actually had an infinity in it, so we knew, aha, I have to take a limit. Okay, this will not. And it may come out in your integral or it may not. You need to be aware of the discontinuities of this function. So I think to myself, okay, I've got a rational function. Where would the denominator equal 0? Well, at 0. So this right here is a discontinuity for this function. So that means I am integrating, I'm finding some area under this function near a vertical asymptote. Specifically, like right here. Okay, so I'm looking to find this area, whether it converges or diverges. Okay, but we need to then set up our improper integral, because this is improper now that we're integrating to a discontinuity. we need to set it up so that, again, we use a limit. And you're going to want to approach the discontinuity from within the limit. So if I take a look at this graph, I am approaching 0 from the right side. So I will let b go to 0 from the right. And that is very important when we evaluate, because when we evaluate this, we're going to get natural log, and natural log doesn't even exist on the left side of 0. So you want to make sure that when you are evaluating, you get the correct direction for your limit. All right, so then my integral is from b to 1 of 1 over x dx. Okay, I keep my limit notation going. And I get natural log of x, make sure you're doing absolute values. Okay, from b to 1. All right, one more step with my limit notation. Natural log of 1 minus natural log of b. Okay, all right, natural log of 1 is 0. And then as b approaches 0 from the right side, the graph of natural log looks like this. So this is, sorry, I'm looking at my notes and realizing I think I might have done the sign error wrong. As b approaches 0 from the right side, natural log approaches negative infinity. So this would be like minus negative infinity. So maybe we would get infinity. Regardless, that's not an answer. That is not a convergent answer. That is not something that we could actually say like, yay, we're getting an infinite area. It doesn't really matter whether we got positive or negative infinity. Our conclusion is that this integral is divergent, like the movie. Okay. All right, so divergent. Anytime I get infinity, my integral is immediately divergent. No matter if, remember, infinities do not add or subtract. Okay, so divergent, 1 infinity, divergent. End of story. Okay, and the last thing, this is where there would be a discontinuity at one of my boundaries. The really tricky thing that you need to be really, really careful and look out for is what if your integral has a discontinuity within the bounds that you were given. For example, let's do the integral from 0 to 3 of 1 over x minus 1 to the 2/3 dx. This is another rational function. We've got some weird exponents, but that's okay. I can see that this is not continuous at x equals 1. That is not either of my bounds. It is not given to me. You just have to know that for yourself. If my integral is not continuous in the middle of my bounds, I need to again split my integral into 2 pieces. So I am going to do a limit and let a go to 1 from the left side. That way I can integrate from 0 to a of this function. And then I will let b go to 1 from the right side. Oh, this is supposed to be b here. b to 3, 1 over x minus 1 to the 2/3. Okay. All right, so again, I looked for a discontinuity. It was in my integral, so I had to split it up into 2 things. If I was integrating something like 1 over x minus 5 from 0 to 3, well, 5's not in my integral, so I don't really care about discontinuities that are not in between my bounds here. I care about the ones that are. Okay, so here, strategy would be a use of. I'm not going to show the use of this time. Okay. And you should get 3 times x minus 1 to the 1/3. Evaluated from 0 to a, plus, again, limit 3 x minus 1 to the 1/3. I guess that's the nice thing about these integrals. If you split it up, it's not like you're doing 2 different integrals. You're getting the same integral out of both of them. You're just evaluating it at different places. Okay, so I'm going to do one thing. I'm going to factor this 3 out of both of them. I'm just going to put it all the way at the front and deal with it later. That way we don't have to worry about it now. Okay, so limit as a approaches 1 from the left of a minus 1 to the 1/3 minus 0 minus 1 to the 1/3. Okay, plus the limit as b approaches 1 from the right of 3 minus 1 to the 1/3. Oh, I need parentheses. Minus b. Let's put some brackets here. Okay, b minus 1 to the 1/3. I put brackets because I wanted to make sure that this limit was evaluated for this term over here too. Okay, so we got 3. Okay, if I let a go to 1, this becomes 0. Hooray! Okay, then what is the cube root of -1? It's -1 times -1 is 1. Okay, over here, I get 2 to the 1/3. Okay, add that on, 2 to the 1/3. And then if I let b go to 1, this also becomes 0. And that's it. That's my final answer. This integral is convergent, even if we integrated around a vertical asymptote. So if you are doing a lot of these practices and you're trying to notice like what is convergent, what is divergent, I encourage you for rational functions like this to look at the exponents. Okay? All right, so take a look at the exponents if you're wondering. If you're not wondering about that, don't worry, we'll get there later. Just focus on your notation for this. This is something that I'm going to be really picky about notation-wise for limit. So when you are doing the homework, when you're filling out the rest of the examples in these notes, practice good limit notation. Okay? And also brush up on your graph behavior. As we saw before, I needed to know what the graph of natural log looked like, what the graph of e to the x looked like, all that stuff. So worth studying for these couple problems. So let's do a quick recap. Okay. So, improper integrals involved integrating either to infinity or negative infinity. To infinity and beyond. Just kidding. So, either to negative infinity or to infinity. Okay? And to combat that, to make it a kind of a proper integral, we ended up using limit notation because we can't plug in infinity technically into a function. So our integration methods haven't changed. It's really the notation about integrating around infinities. Okay, if we said that we were able to evaluate the limit and we got a real whole number, we said that the integral converged. We've also integrated over the entire real number system from positive infinity, or excuse me, from negative infinity to positive infinity. We evaluated that by splitting it up into 2 parts. One, and we got to choose where we split it up. Notice we had to choose the same place because we're like literally dividing it in half and just evaluating one half and then the other half. Okay, you get to choose. Be smart about your choice. 0 is usually a good choice, unless 0 is a discontinuity for whatever function you're dealing with. Okay, but when you split it up, even though we integrated over the real number system, we still got something convergent. Okay, and the last thing we did was we thought, okay, what if we integrate a function around one of its discontinuities? That way you had to know that yourself. Nobody's going to tell you that there is a discontinuity for this function. So you need to make sure that you are thinking about, how do I know if a function is continuous or not? How do I find the discontinuities? Maybe setting the denominator equal to 0 is a good start. Okay, we dealt with it the same way we would deal with integrating to infinity or negative infinity. We made a limit and replaced it with a variable. We wanted to make sure that we approached the number we were talking about from the correct side, from within the bounds of the integration. It helps you to sketch this interval or just write it out, 0 to 1, and think about, okay, I'm approaching it from this side. Okay, then that would be the right. Notice the left side is not within the bounds of our integral, so we would not want to evaluate coming from the left. Okay, but we evaluated it, and around a vertical asymptote we could get divergent. Possible. Anytime we get even one part that goes to infinity, it diverges. Okay, however, we could also integrate around a vertical asymptote that was not given by one of our bounds. So somewhere like, and this is not what this function looks like, but something where we were, yeah, something like that. That's not what that looks like. I should pull out my calculator and actually graph it. But integrating around a vertical asymptote somehow, and we split it up like we did with the integrating over the whole real number system. We made one limit for the left side, one limit for the right side, and evaluate it. And we could get something convergent. Okay. All right, so improper integrals, our integration techniques have not changed. Our notation for where we're integrating has changed. We've changed from having something be integrable only if it exists everywhere between the bounds, to broadening that idea where we could integrate anywhere we would like in the real number system.